Hello, and welcome to SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute. Welcome to our viewers from around the world. Thank you for joining us. Please let us know where you are watching from. Also, welcome to listeners on the podcast version of SETI Live, available on most podcast platforms. Today, I am excited to welcome in astrobiologist Betül Kaçar, who is doing some amazing work at her own lab through the University of Wisconsin-Madison. And we're here to talk about what they have called a cookbook of life, which I just think is a fascinating title to begin with. But basically, your team identified 270 self-replicating chemical reactions that may have sparked life and could do so not just here on Earth, but on other planets. And so I'm really excited to talk to you. So Dr. Kaçar, welcome in. Thank you for being here today.
Thank you for having me.
So what if life isn't rare at all, but inevitable under the right chemistry? That's sort of the question that you're asking here. Tell me about this research. Just tell me something, get us into this, because I am not a biologist. I am not a chemist. I only play one on TV very vaguely. So give us an introduction to what this work is.
Well, you all are listening to this, so you must be into this somehow. I hope I don't need to convince you that this is the time, right, to be thinking differently about life and really thinking about possibilities more broadly. Universe is rich with planets that are radically different from Earth. We now know this, and
Mm-hmm.
to think what we know about our universe that we didn't only 20 years ago is mind-blowing. If we were to discover life as we do not yet know it, we must challenge our deepest assumptions and even maybe reconsider the atoms and elements that make life possible at first place. And that's where this research comes from.
So tell us about your lab, the Kaçar lab. I'm absolutely impressed that you have a lab named after you, that you have your own research place. How did this come about, and what is the focus?
Yeah, we are in a biology lab primarily, and I think that puts us in a kind of a unique position in terms of astrobiology. Even though half the term contains the biology, I think biology-focused groups have been lacking broadly, and that there's a historical reason for this, and we can get into that. But we are primarily thinking about evolution and an early evolution of life, and we approach sort of reconstructing and rebuilding and recreating our own planet's past and the biology that once lived on this planet through combining tools from biology, chemistry, computation, bioinformatics, so on and so forth. So I can tell you that we are doing two things. We are trying to travel back in time by using what we know now about life, but at the same time, we are trying to go forward from past and try to recapitulate early prebiotic conditions and think about what were the alternatives to life as we know it.
Okay, so let's start kind of at the beginning then. Let's talk about the past. Why, one of the focuses of the SETI Institute, of course, is the origin of life. Why is this such a hard problem to solve?
Well, this is also a hard question. Even why it's so hard is a difficult question. Look, you can just we know that okay. We first let's just think about a cell, right? Life starts with the establishment of cell, at least on this planet, and now imagine the most complicated, maybe the most complex machine that we've ever built, or could even imagine building. Even the simplest cell is way more complex than what we can imagine that we built in terms of a machine. And the simplest cell we know comes from rocks, comes from water, and comes from atmospheric gases. We could watch rocks and gases for 1,000,000 years together, you and me, and never see anything like a living cell. So we're literally missing something really important in the earliest and the first formation of cells that we can think about them. And arguably, we don't even need to have to go to the cell. Some of the molecules themselves are extremely complex that we couldn't build them or do what they do even if we tried. And there are literally thousands of them. So I must say that fundamentally, it does sound like a chemistry problem,
Mm-hmm.
but in integration and thinking a little differently about our assumptions and the fact that we are now barely starting building down those walls that I think kept these disciplines apart from one another for so long is maybe what makes the problem hard.
So I'm going to take just a quick, I want to get back to this, but let me welcome in people who are watching. I have someone who says they're just watching from the USA. Welcome in. Santa Cruz, I'm guessing that's actually not Santa Cruz here in California. Switzerland, Italy, Michigan, Nigeria. Wow, welcome in from Nigeria. That is, I think that's kind of a new one for me. Thank you for being here. Okay, so what are some of the assumptions that you've kind of had to face in this research?
Well, we can start from the very beginning, the building blocks of life. And we know that life is carbon-based, but we don't necessarily know if the initial conditions required that, right? I think recently have been started thinking a bit more agnostic about the chemistry that would compose life early on. And I think a fundamental lack of understanding of evolution or integration, let's say, with evolutionary biology. Literally, we have not put life into origins of life yet. And I think that is perhaps causing some problems too. We now know that you can build all the molecules you want. We are able to simulate certain atmospheric conditions, generate these molecules. That's one thing, and we are very good at that. But it's another thing to make these molecules react with one another in a way that they start exhibiting a lifelike property. And that's a challenge, and that won't happen until we distill that the lessons we learned from evolution and from evolutionary biology in particular, and apply them within the context of prebiotic chemistry.
Oh, okay. This is when we say this is the big question, this kind of really is the big question. So let's talk about this specific research. So this cookbook of life that I'm absolutely fascinated by. This actually came out in 2023. Betül and I have been trying to make this happen for a while. And finally,
I know. I just realized that it's been. Oh yeah, thanks for being patient.
Yeah, no worries. This is that when you emailed me and said, "Hey, we should do this," and I thought, I'm still excited. I also couldn't believe it had been 2023.
I was happy that you replied to my email, which was in reply to your email from a year ago.
It's all right. I'm just happy you're here. So let's talk about this cookbook. So what exactly did your team discover? Because this isn't just you. You have a team. So what did your team discover for this?
Yeah, that's a very good point. Nothing in science happens in isolation. We are at the frontier talking about this, but yes, there's a big and very interdisciplinary team actually that built the work that I'm sharing today. As I mentioned early on, the current search strategies, and this is arguably like the most logical way to go, are constrained by life as we know, and they're constrained by Earth's carbon-based blueprint. We basically try to understand the scope of life and the chemical possibilities of life, and explore how life might emerge under very unfamiliar planetary conditions, using molecules and maybe environments that are quite alien to our own known biosphere. So that's where this thing comes from, and I think that got your attention too. That we sort of we discovered over 200 different reaction sets that I will explain in a minute, that we think are self-sustaining, self-amplifying chemical reaction networks, and they are composed entirely out of inorganic components. So that's I think what's enabling our conversation right now too. Happy to get into the details, of course.
Yeah. Okay. So this is where I get a little lost. So you're going to be explaining for me as well. But let's talk about autocatalytic and comproportionation reactions. So that's kind of the heart of these chemical reactions that are self-sustaining. So that's the autocatalytic, I'm assuming. And then, but explain it to me like I'm 5. What exactly are these types of reactions?
Well, sure thing. So first of all, not a big fan of the comproportionation name myself. Okay, all the new words I have to learn during origin of life. Anyway, but you can think of disproportionation, and this is sort of the opposite of disproportionation. All right, so I'm gonna get into that in a minute. But let me beforehand say that when we think of life and when we think of origin of life in the most simplest term, and if you were a 5-year-old, I would tell you that it's like a bar stool, with the hopes that you won't know what a bar stool means, the hopes that no one took you to a bar at 5 years old, all right? but I hope that you would understand what I mean when I say it's like the bar stool, and each legs are formed by a certain component, and in this case, a cellular component that altogether forms life. We are not the first to think of this. The Ganti and Chemoton, if people are interested, they can read about this from the 60s. There is great papers that talk about metabolism, informatics, and environment altogether composing life. And by the environment, I don't mean the planet itself, but I mean the compartment. So there has to be a way. Life has to eat and life has to poop, right? So that it does that. That's the metabolism. Everything eats, everything poops. That's what life is. And there has to be some sort of informatic system that enables this eating and pooping process. That's information. And these two has to happen within some sort of containment, and that's what we refer to as the compartment. So we're really looking for this triangle, all right? We're looking for each of these things to get together, and the field has been tackling these from maybe discrete ends separately. Some groups are trying to recapitulate the origin of information in the form of RNA, different informatic molecules. Some people are trying to understand how this eating and pooping has happened through research through metabolism and hydrothermal vents and whatnot. Some people look at the compartments and how these cells, like protocells, may have formed and create this early containment. So our initial research tried to break from this division in a way that it's not a matter of which leg evolved first, that why can't we just collectively think about these three as an emergent phenomenon, as a collective, instead of three separate phenomenon, basically. So that's where the research starts. My lab looks into all of these legs separately through experiments, and at the same time try to think about the emergence between these three collectively. I'm going to pause now for a minute in case you have a question.
So many questions. Wow. Okay. So your lab is sort of doing what I would say is that more holistic approach of sort of, looking at all of the pieces of the puzzle and not just these separate pieces. So that's really fascinating to me. Okay. How does this change our understanding of life's potential? So what does this do for just sort of like understanding how life came about so far?
I don't think we even know we don't have an understanding of life's potential, let alone we need to first understand that in order to change that, right? I mean, was it Lynn Margulis that put this the best, saying that we don't understand, we cannot separate a dead cat from a live one, right? Biology doesn't understand the difference between the two. So we are like second graders when it comes to understanding life. So it is not that, we are not yet, we should not get ahead of ourselves as we are not knowing anything yet. So that's the baby steps, and we got to be careful about that. But my lab does a lot of different things, but we take currently existing organisms, and these are bacteria, microbes. We engineer them, try to reprogram them so that they exhibit behaviors that are familiar to them from their past. So we try to resurrect their own ancestry and history at one level. At the same time, we are building these legs of the bar stool. So we're trying to rebuild a protein from scratch. We're trying to make metabolisms from scratch. And the research that you're highlighting here comes from that drive, that can we figure out the earliest pathways that enabled life to eat and poop.
Right.
Pardon my French, but that's what life does. No shame. So we started from a very expanded view of the network of biochemistry. As I mentioned, metabolic networks, obviously biologists from very different angles has been studying these metabolic networks for like over 20 years. But we wanted to add that level of information on top of metabolism. Instead of seeing them as two separate phenomena, what are the bridges, what are the overlaps between, say, RNA world dictated origin of life view versus metabolism first dictated origin of life view. And sort of that's when we realized that at the core of this is what we think of the autocatalytic cycles that are common and that are formed when translation is added to the metabolism. It's a behavior that is common regardless of where you are within this bar stool.
Okay.
Right.
I'm gonna welcome in a couple more people. I was corrected. The person in Santa Cruz isn't Santa Cruz, California. Go banana slugs. Someone from Colorado, my home state, welcome in. And oh wow, Libya and Latvia. Wow, we are getting some nice places here. And New Hampshire. All right, fantastic. Thank you everybody for joining us. Okay, let's.
Let's talk about autocatalytic cycles. Let me get into that.
I was going to say, can you kind of like walk us through an example of one of these reactions in a way that we'll all understand, that doesn't require me to have a chemistry PhD?
All right, I can say that so imagine you're throwing a party and you invite people and you tell them that you want them to invite others. So the people you invite will invite more people, those people will invite more people, and suddenly the party is big and it's complex. So the party is constantly growing because each person you invited to the party is inviting someone else. That's really what autocatalysis is. So now don't think person inviting another person, but it's a molecule inviting another molecule and inviting another molecule. So the whole system is sort of growing by itself. I think in the most simplest way, that's what I could think of right now, a party metaphor. Now, as I like to think, not every crowd makes a party, right? Could be a total mess. So there needs to be some sort of behavior, some sort of pattern in which these components interact. So what makes autocatalysis interesting is that these networks, going from the party metaphor, there are some behavior that are maybe certain groups that interact more than the others. But the idea is that the products catalyze the production of other starting materials. And at the root of it, that's what life is capable of doing this. And that's why we think that autocatalysis is a defining feature of life on Earth. They drive growth, they drive resilience, they drive evolutionary behavior, be it adaptability or however it may proceed.
Oh, it's just such a big question. It's just such a massive piece of research. I'm kind of floored. Okay, let's talk a little bit more about you and your view and what you're working on. Does this research change how you're viewing life in the universe and the ease or difficulty with which it may form?
Yes, certainly. I mean, what we basically realize that not all reactions need to run on organic carbon, right? That's a big, I think, I guess, challenge to the current view, because life is carbon based. What we find is that these sort of reactions are more prevalent than we previously assumed across the periodic table, and a lot of inorganic components, inorganic chemicals basically are capable of this sort of life-like behavior, at least based on our initial calculations. But that's I think quite interesting. That's we can actually think beyond the whole carbon-based life, I think, in a way that welcomes other molecules and other components, which I think is quite exciting for thinking about life's possibilities, especially considering how diverse different planets are, their atmosphere are, and their surface composition might be. But let me just briefly describe what comproportionation is. I mentioned the opposites of disproportionation. As I mentioned, autocatalysis, its party may get more fun as you invite more people who invite more people. That's really what this is to it. Integration, and you then realize there's more maybe stability, there's more mutualism, there's maybe competition, there's cooperation. So you start seeing this interaction within this party metaphor, but that could be applied to molecules as well. Molecules do this. So the field has been trying to create chemicals and chemical mixtures, however messy they might be, that exhibit these sort of behavior. What we presented in our paper, published in JACS, and also made it to the cover, which was awesome. That's comproportionation reactions. You can think about a cycle of reactions that doubles one of the compounds. All right, so we are not thinking about If you have $50 and I have $50 and we combine it, that's $100. And if we give this, we share this $100 equally, then the next cycle has $50 each. That will be comproportionation. If I take that $100 and give you back zero and keep all 100 to myself, that is disproportionation. So comproportionation equally distributes, basically. In our case, it's not dollars, but it's redox state. It equally distributes that redox state across compounds. So you basically get that propagation across many, many cycles. So you can imagine building a self-sustaining chemical system from a huge variety of chemicals in this context, and not just carbon. Challenging the view again that life could have got started as a self-replicating chemical system made out of, for example, sulfur or boron or something, and not necessarily carbon, and may have integrated carbon later. Or you can also think that other planets with more bizarre forms of life that are maybe a mix of carbon and something else may also instigate different forms of life. So it opens a bunch of new possibilities in that regard.
I like this. So just for the audience, when you say redox, you're talking reduction oxidation equations, which if you've ever taken chemistry, I'm sorry. But
hey, it's fun. If you're taking chemistry and you did not like it, maybe it wasn't told you in the fun way. Let's talk about it that way. Let's put it on the teacher.
Fair enough. My chemistry teachers were actually in college were lovely, and I actually really enjoyed it. But I like math, and so for me, redox equations are really just, they're math. It's this needs to go here and here and balance things out, and that's basically what we're talking. Okay, so we have a few audience questions, and I think there are a couple that I want to ask. So this is sort of kind of the heart of it. I think one of the things we kind of talk about when we talk about this origin of life, and we always say like, okay, well, we have these chemicals, we have some sort of chemical mixture, we have water, we have heat, but how does this make life? And Space Frog is asking, is it we can't recreate it because we're missing a key component that may have decayed away or is no longer available? Do we have any sort of ideas of what perhaps, and it may be more than one missing element here, but do we have any ideas what we're missing from this equation?
Yeah, this is a great question, and I see you, Space Frog. So it's that's a nice name. Yes, and some, when we think about what sort of, for instance, applications or breakthroughs or technologies also can come out of studying these problems, that's exactly the heart of the problem, right? Can we think of lifelike systems that with no precedent in biology, and this sort of exploration enables generation of that self-sustaining lifelike chemistries that not only are critical for understanding how life might arise elsewhere, but also makes you think about cell-free manufacturing and developing this sort of biosynthetic components that are capable of producing non-biological compounds with applications in sustainable chemistry and synthetic ecology. So the fact that life indeed may have used really early on components that are no longer available opens up just a vast array of research problems that can keep us busy for centuries, and it also has a lot of benefits in return in terms of the way we use biology and chemistry for our own good. So that's a fantastic question. Thank you.
Okay. And I'm going to take this last one because I know you have to run. The last mage on Earth is asking, is life more likely to form underground with pressure or on the surface of worlds? So we've talked a little bit about heat and chemistry and that kind of thing. Does pressure add into this equation at all?
Yeah, we have to think about the environment. We have to think about the feasibility, chemical feasibility under a variety of different environmental conditions. I don't think we can answer this question very clearly with knowledge we have right now, with what we know. What we can speculate, however, is that by understanding the breadth of different chemistries that life is capable of carrying out, may liberate us from narrowing or constraining the environment a little bit. It may be more broader than we think. Instead of thinking about, is it surface? Is it the bottom of the ocean? Is it the top of a volcano? It is more about how can this chemistry be sustained. And I agree with you, because sustaining a chemical system demands thinking about stability, and that comes with an environmental understanding that will maintain that stability. So I understand where this question is coming from, but I don't think we need to constrain ourselves to the environment. Because we understand to some degree what these diverse environments are, we have to think about what different chemistries may be possible under a variety of different environments instead of narrowing them to one or two.
Okay, that makes sense, and I like that. I like that. I do feel one of the fundamental problems, of course, of searching for the origin of life and searching for life on other worlds is we have one planet with life that is our example that we can use as sort of the research base for it. And so there's a lot of assumptions from our planet, from our solar system, even, that we've had to sort of go, oh no, it's not necessarily how everything else works. So
I don't think, again, first of all, there's no one life on this planet either. If you think about what life has gone through, we're learning over and over again that our planet has gone through a lot of alien phases in its own right.
Mm-hmm.
And life 3 billion years ago and planet 3 billion years ago is arguably a completely altogether different alien place for us too. So when we think about life's past, and I'm not just talking about origin, that's one problem, but what life did after that is another problem. How life survived these planetary extremes is another problem. So each of these transition points lead to a different form of life for us to explore and think about. And by thinking big, by thinking broadly, and thinking about how we can then connect our experimental abilities with our interpretations and models is arguably what we need in order to make more use of and squeeze everything we can out of this n equals 1, because it is actually more than 1 if you think about it.
Right. Fair enough. Fair enough. So I know you have to run. What's next for you, for your team? What are you working on now?
Lots of things. Lots of things. We are doing a lot of experiments. We are primarily a lab-based lab, so we are now testing these systems through very exciting collaborations. We have a completely different NASA center that is on understanding how life learned to eat and how it chooses what it does. So yeah, there's a lot going on. There's never a dull moment in the lab, for sure.
Well, I'm looking forward to hearing more from you. I definitely want to have you back. So let us please stay in contact so that, and if you have any of your team that you would like to have on, let me know that as well. Thank you, everybody, for joining us today. We are the SETI Institute. We are a 501c3 nonprofit. So if you want to help us keep running these programs, I'll head off to our website, seti.org, and click on the bright red donate or give now button. Thank you, everybody, for watching. We also have an e-news you can sign up for. Like, subscribe, comment, share, do all of the things, and follow us for more science. I will not be here next week, but Frank and Simon will be here to give an update on Laser SETI. So we have a new location to talk about and a display in London. So it's a very big deal. Again, Dr. Kaçar, thank you so much for being here. Greatly, greatly appreciated. And we will definitely have you back on because there is so much more to talk about on this research.
For sure. Thanks for having me.
Thank you, everybody, for joining us.